Hello everyone, today we're talking about logarithmic functions, section 4.2 in our book. So first thing I want us to do is express the equation in exponential form. Here we have it in logarithmic form. So to get it in exponential form, my sheet went away. To get it in exponential form, how I want you to think about it. This number here will be the base of my exponent, just like the base of my exponential functions. This number here is going to be my exponent, and then this number is going to be what my exponential function is equal to. So if you check, 3 raised to the 4th, in fact, equals 81. And again, I'm going to write this logarithmic equation in exponential form. So the base of the log becomes the base of my exponent. Whatever I was equal to becomes my exponent. Oh, and I wrote it backwards. And whatever was with my logarithm is what I am now equal to. And if you check, 8 raised to the 2/3 will give you 4. Okay. So now we have it in exponential form. They want us to write it in logarithmic form, so just go backwards. So again, this was the base here, so that's going to be the base of my log. This is what we were equal to, so that is included in my log. And then now this equals negative 3/2. Okay, so the base of my exponent is the base of my log. Whatever I was equal to before becomes part of my logarithm, right? It's my x of the logarithm, if you want to think of it that way. This is the base of my log. And then whatever my logarithm is equal to, that is the exponent in my exponential form. So now, same thing over here. 7 is my base. 343 is my x, right? That's 343 is the part of my logarithm. And then the exponent 3 is what my expression, what my function is equal to. So real basic, just rewriting from exponential to logarithmic, and then from logarithmic to exponential, and then from exponential to logarithmic. Now they want us to evaluate this expression. So they've given us 3 different logs, and they want us to evaluate it. So they don't say it, but what they really mean is, what is this equal to? Right? So what is log base 5 of 5 raised to the 4th? Well, your calculator can't do this, because your calculator can't do logs base 5. Your calculator, when the log button in your calculator is only base 10. So your calculator only knows log base 10, so your calculator can't solve this, but we can. So I'm just going to rewrite it from logarithmic to exponential. So the base of my logarithm becomes the base of my exponent. Whatever I was equal to becomes my exponent. And then whatever my x was, whatever was part of my log, right, whatever I was taking the log of, right, because this is the base 5 of 5 to the 4th, is what I am equal to in my exponential form. So now you can easily see, okay, x equals 4. So if my calculator could evaluate log base 5 of 5 raised to the 4th, I would get 4. Okay, same thing here. They don't say it, but that's what they're implying. Okay, so my base is 4, my exponent is x, and that's equal to 64. Well, 4 raised to the what gives me 64? Well, I could rewrite this as 4 to the x equals 4 to the 3rd, so x equals 3. So I've evaluated that expression. If my calculator could type log base 4 into my calculator, if I did log base 4 of 64, my calculator would tell me 3. And finally, log base 9 of 9. So 9 raised to the x equals 9. Well, 9 is basically just 9 to the first, so x equals 1. And again, if my calculator could do log base 9, it would tell me log base 9 of 9 is just 1. So there we evaluated some logarithmic expressions. Now we're going to use the definition of logs to find x, so pretty similar, except our x's are maybe in different spots than just equal to x like they were here. So here we can see they're in different spots. So it might take a little bit more finagling with our rules, with how we write logs into exponential expressions to get the actual answer. So in this one we can see, okay, 10 is my base, 2 is my exponent, and it's equal to whatever I'm taking the log of. So I'm doing log base 10 of x. Your calculator can't do this because if you don't know what you're taking the log of, your calculator doesn't know what to do, but we can do it. So log base 10 of x equal to 2, our x would have to be 100. Because 10 squared is 100. Calculator can't do that, we can. Same thing over here. I've got base 5 squared equals x. Remember, this is going to be the base of my exponent. This is going to be my exponent. Whatever I'm taking the log of is now what my exponential expression is equal to. So here, x equals 25. That's all there is to it. This, I would like us to have down. This goes back to the basic functions that we learned of exponential functions. So if you could get, this is the basic log base 10. Okay, what is important to know about this is it crosses through the point 1, 0. If you'll remember, the exponential graphs, the basic exponential graphs, cross through the point 0, 1. So now instead of going through the y-axis, here we've gone through the x-axis at 1, 0. So that's the difference between exponential and logs because they're inverse functions of each other. And we'll see that coming up in later chapters. So now the key thing here is it goes through 1, 0, and since whatever the base is, right, so like for instance at 1, and the graph doesn't go all the way out there because I wasn't able to clearly copy that well, but at 1 it would cross at 10, 1. Right, so whatever the base is, it's going to cross at y equals 1. So if I had log base 5 of x, then it would cross at 5, 1. Right, so whatever the base is, it's kind of just the opposite of the exponential functions. Right, if I had an exponential function, and when I went 1, when my x equaled 1, my y would equal whatever the base was. So now, whenever y equals 1, x is equal to whatever the base is. And this could be log base 4, log base 3, doesn't matter. Either way, we're going to cross at when x equals the base, y equals 1. Okay, and then I've also included the ln of x. ln of x, like I said before, is just the inverse function of e. So ln of x also goes through the point 1, 0. And you can see when y equals 1 that it crosses at 2.718, which is what e is equal to. So ln is really base e. Okay, so at 1 it crosses 2.718, which is what e is equal to. I've been saying that all along, how e is just a number. Don't let it freak you out. E is just a number. It approximately rounds to 2.718. So you can see when y equals 1, it does cross the base, just like it does for logarithms. This is just in base e. And you'll see that connection when we get later on in the chapter. So, I wanted you to notice these are just the basic functions. We're going to take and we're going to do transformations to these, just like we did with the exponential functions. And I wanted you to know that y equals ln is the inverse of the y equals e to the x function, right? Just like y equals log base b, whatever b may be, is the inverse of y equals b to the x, whatever be for any number b. Okay. We can change this 3, 5, and it's going to be the inverse of the exponential function. So, graph the functions only using the basic graphs. So they want us to graph this function, and they don't want us to use our calculator. Our calculator can't graph log base 3 anyway, so our calculator really can't graph this. But if we had a log base 10, all they want us to do is graph the function using the basic graph. So let me insert. So I'll do the original graph first. So if I was just taking, so the original graph, I'm saying let's just say y equals log base 3 of x. So as I was explaining in the previous slide, y equals log base 3 of x, well, it's going to go through 1, 0 instead of 0, 1 because I haven't shifted it yet. This is just the original. And at x equals 3, it'll go to a y value of 1. And then when x equals 9, it'll go to a y value of 2. Right? 3 squared is 9. So it's like the opposite of the exponential, right? They're inverses of each other. And then, in this case, our y-axis is a vertical asymptote. We'll never cross the y-axis here. So it's important to note that logs will never have negative values unless obviously we have negatives involved here with a reflection or something over an axis, but logs will never be negative. Okay, so that's the original. Now let's see what happens after we do the appropriate transformations. So I like to start at 1, 0, right? Because that's going to be the same for typically all logarithms. So I start at 1, 0, and then I'm going to do the transformations to that. Then I'll graph it from there. So that -1 in with our x means I'm shifting right 1. The -2 outside means I'm shifting down 2. So now instead of starting at 1, 1, I've shifted right 1 and I've shifted down 2. So now this log base 3 of x minus 1, all subtracted by 2, goes through this point here. And then, since it's log base 3, I go up 1 over 3. Just like I did here, up 1. Sorry, that should go through, not up 1 over 3, but it should go through at 4, then it should be at -1. Okay, so it went up 1 over 2 here, because at 3 it should equal 1. So here we've gone up 1 over 2. And then again, same thing here, up to over 8. So we've just taken these points and we've shifted them down. And actually I realized it was shifted down 2 and right 1. So down 2, right 1. This one should be shifted down 2, right 1 as well. So this one should be over here. And then my vertical asymptote is now going to be the line x equals 1. All right, so we have a vertical asymptote here, this line never crossing 1. Okay, so now you should be able to do the example problems that accompany this on the PowerPoint, and we'll talk about it in class tomorrow.